All right, so like I said, chemical reactions can vary in their length of time for completion. It depends really on two things. It depends on the characteristics of the reactant, so that could be something like what phase they're in, or are they ionic, or are they not ionic? And it also depends on the conditions under which the reaction is run. And so you probably can imagine that if you change the temperature, reaction rates will change. They usually go faster. The pressure can affect the rate, things like that. So by understanding how the rate of reaction is affected by changing these conditions, we're going to learn more details about what's happening at the molecular level. So that's kind of at the end of this chapter. We talk about what's happening to the actual molecules. All right, so what are we going to look at in this chapter? How is the rate of reaction measured? What conditions will affect the rate of reaction? How do we express the relationship of rate to the variables affecting the rate? Things like concentration, temperature, etc. And then what happens on a molecular level during a chemical reaction? Okay, so the study of reaction rates is called chemical kinetics. So the study of reaction rates, how they change under conditions, what events happen during the reaction, this is all considered chemical kinetics. What are some variables that affect the reaction rate? We've already talked about some of these things. Think about them before you go on. Maybe stop it and think about it. Some things, I think we talked about temperature. Let's see. Okay, the concentration of the reactions is very important. The use of a catalyst can speed up a reaction. The temperature, like I said, and the nature of the reactants. These are all things that can affect the reaction rate. All right, so let's first talk about concentration of reactants. And you know this in a general sense. If you light a match in a room, it'll ignite. Because the match is reacting with oxygen. But what if you reacted it in, right next to an oxygen tank, or like where the valve was open and you're in a very much higher concentration of oxygen? It would likely explode. So the reaction rate can go much faster depending on the concentration. So most often the rate of reaction will increase when concentration increases. What happens when a reaction takes place, you have to have a collision between molecules. In order for them to react, they have to come in contact with each other. So it should make sense that the more molecules you have, the more likely they're going to collide with each other, and the more likelihood of a successful collision or a reaction. So the more you have, the more collisions, the faster a reaction can go. It is true, though, that some reactions are unaffected. The rate is unaffected by the concentration, and it just has to be present at some level. And actually, by the end of this chapter, we'll talk a little bit about this. It will depend on the reaction and the steps that occur during a reaction. So you can't always, I've just put it out there right now, because you can't always tell if a reaction will increase with concentration or not. So in general, you can imagine it does, but not always. All right, use of a catalyst. First of all, what is a catalyst? A catalyst is a substance that increases the rate of a reaction without being consumed in the overall reaction. So it's something that gets used but then is replenished or is untouched throughout the reaction. And so what happens, generally speaking, a catalyst, and we don't usually write it in the overall balanced chemical equation because it doesn't get used up, or it's not really produced, it's just there. So sometimes it's written, sometimes something is written over the arrow of the equation, and that it indicates a catalyst or something like that. But generally speaking, what happens, so yeah, here's an example. 2H2O, and then the HBr is the catalyst that makes that reaction happen. Usually what happens is that the catalyst reduces the activation energy, which we haven't really talked about yet, but it reduces the amount of energy needed for a reaction to happen. Usually it does that by providing another pathway or providing a region for something to happen. Again, we'll talk a little bit more about this at the end of this chapter. So like I said, sometimes it can provide an alternative pathway that results in a faster rate. Okay, so the temperature at which a reaction occurs is probably something you would have come up with first if I asked you about it. What affects a rate? So almost always the reaction will speed up when temperature increases. A good rule of thumb is that the reaction doubles for every 10 degrees rise in temperature. We'll talk more about this later too, but you can sort of imagine what's happening, that if you increase the temperature, what happens to the molecules? Molecules move around faster. So if they move around faster, there is a higher probability of them colliding with each other. And so that's usually why the temperature affects the reaction. All right, and then finally, the nature of the reactants can also affect the reaction rate. Things like the phase that the reactants are in, or if they're ionic or not. So, for example, if a reactant is a solid, then the surface area has to be considered, because especially if they're in two different phases, they need to, the area where the reaction takes place has to be considered. And so not increasing something may not affect it if the amount of surface area where the reaction occurs doesn't change. Charged particles, like I said, ionic particles, because they're attracted to each other, they will react faster than molecular compounds that are not charged. And polar will react faster than nonpolar for the same reason. It's because there's already something attracting them, and so the collision is more likely to happen if they're already attracted to each other. And then similar to having different phases, even if you have the same phase, two liquids that aren't soluble in each other, they again can only react where in the areas where they touch. And so these are just some considerations in why the nature of the reactant can also affect the reaction rate. All right, so what is a reaction rate? Well, a rate is always a measure of amount per unit time. So you can call say the reaction rate is the increase in the amount of a product formed per unit time. You could actually also express it as the decrease in the amount of a reactant used up per unit time. So either way, you can look at it from either direction. But always the time rate always has an amount of time in there. So and the time could be if it's a very fast reaction, you might say how many moles per second. If it's a very slow reaction, it could even be how many grams per year or whatever. So the unit of time is always important. Generally, at least in this course, we're always going to be talking about the molar concentration, and the symbol to indicate molar concentration will be whatever the compound is in brackets. So if you see brackets around something, that means molarity, the concentration in units of molarity. All right, so let's look at this decomposition of nitrogen pentoxide. You can see N2O5 breaks apart into NO2 and O2. We can denote the molar concentration by using brackets. So we can say, all right, what is the concentration of O2? That would be O2 in brackets. And then when you see that delta symbol, what we're saying there is, what's the change in O2 concentration? So delta means change in, and so when you see delta O2, you're saying, what is the change in O2 concentration? The change in O2 concentration is always the final concentration minus the initial concentration. In this case, because O2 is a product, delta O2 will be a positive number. It'll be increasing. If we were talking about a reactant, then the amount of reactant would be decreasing, so delta O2 would be negative, or delta N2O5, sorry, would be negative. It's always final minus initial. So now if we are, we can also look at a time interval. So delta T would be the change in time, and delta T is always the final time minus the initial time. So if we want to measure the rate of O2, we would say delta O2 divided by delta T. So what is the change in O2 concentration over the change in time, and that gives us the rate. So rate always is change of concentration over change in time. And it could be, like I said, it could be per minute, could be per second, whatever. And of course, the time doesn't have to be just one. You can use final minus initial. So here you can see that delta O2 over delta T is the same as final concentration of O2 minus initial concentration of O2 divided by final time minus initial time. So if you're given a bunch of data, you can always figure out the rate of reaction by plugging it into this equation. Now, if you allow delta T to get shorter, the smaller and smaller delta T is, the smaller and smaller your unit of measure is. And if you've taken any calculus, you probably recognize this as the smaller and smaller delta T gets, the more instantaneous your rate is. So it's the rate at a particular instance. And this is the same as finding the slope of the line tangent to the curve if you plot time versus concentration. So I think that's on the next slide. Right, so here we have time on the x-axis and concentration on the y-axis. And notice that the concentration is increasing because, again, we're talking about O2 as a product. So it should be it starts out at 0 and then it's increasing over time. So you can actually find the rate of reaction over any segment of time. You could take, the whole thing. You could say the concentration at 6,000 seconds is about 0.0075 minus the concentration at time 0. So you could take that divided by the total amount of time, 6,000 minus 0, and you could find the rate of reaction for the whole 6,000 seconds. Or you could take any small segment. You could take the concentration from 1,200 seconds to 2,400 seconds or whatever. I think this will show up on the next slide or two. But anyway, what this slide is showing you that if you take the tangent of any point, you will find the instantaneous rate at that particular moment in time. One thing you might notice about this curve is that it is it's increasing, but over time, notice that the red line is getting flatter and flatter and flatter. So at the beginning, the rate is going very fast. The O2 concentration is increasing very quickly, and then over time, the O2 it's still increasing, but it's increasing at a slower rate. So that if you clock a reaction, and you're probably familiar with this if you watch a reaction over time, eventually it slows down and so the rate decreases. If you were to take the tangent at any point, you would see that at first it would be very steep and then it would start to level off, which means it's getting slower. All right, so this is what I was just talking about, was that last figure. So again, the rate decreases as the reaction proceeds. So even though the O2 continues to increase, the rate at which it increases decreases. Well, and why would that be? Well, if you sort of think of the whole thing, the whole reaction, the reaction starts out fast. You've got a lot of reactants, and they can all collide with each other. As those reactants get used up, you have fewer and fewer of them. What happens when the concentration goes down? Well, you have fewer collisions, and so the rate slows down. So over time, because your reactants get used up, the reaction will slow down. All right, so here was what I was talking about earlier. So you can actually find the slope of any particular point on the graph. And so this actually shows you two different rates. So if you look up at the lower triangle, which is toward the left, right around 1,200 seconds. You can see that we just picked 2 points there, and we could find the rate of reaction by taking the change in concentration of O2, which would be approximately all the data is over here on the right. So at 1,200 seconds, it was 0.0036, so that would be final. At 600 seconds, it was 0.0021, so you take the difference, 0.0036 minus 0.0021, and that gives you 0.0015. You divide by the amount of time, which is 1200 minus 600 seconds, so the total time, delta t, is 600 seconds, so 0.0015 divided by 600 seconds gives you a rate of 2.5 times 10 to the minus 6 moles per liter per second. Then notice the top triangle. So if you figure out the rate at the, which is sort of going from about 4,000 seconds to 4,800 seconds. Again, now you can read the concentration off of the graph. Oh, it's 4,200 to 4,800. So 0.0075 minus 0.0072 gives you 0.0003. Again, the unit of time is 600 seconds. Again, so you divide by 600 seconds, and you can see that the rate of the second point, the second slope area, is 5 times 10 to the minus 7th, and clearly that is smaller than 2.5 times 10 to the minus 6. So anyway, you can, if you're given data, you can find the rate over any segment of time, and again, the smaller your unit of time, the more instantaneous that rate is. Oh, so here is all the, if you go back and listen to what I was saying, here's what I was just saying. If you find the rate over the two different intervals. Okay, so it does get a little bit complicated. You could find the rate of any one particular compound in a reaction, and it won't really matter if you're only focusing on one reactant or one product. But if you're trying to relate the rate of one substance to the rate of another substance in a reaction, you have to be really careful because some of them are disappearing, some of them are appearing, and stoichiometry, the amount is different. So let's start with back the same equation. The rate of decomposition of N2O5 is given as this equation. So it's the change in concentration of N2O5 over the change in time. But by convention, we always want our rates to be a positive number. And so because the N2O5 is decreasing, and because it's a reactant, we put a negative in front of it because eventually our answer will be a positive number. So the rate of something that's a reactant will always have a negative in front of it. And it'll be the change in concentration of N2O5 or whatever you're talking about over the change in T. So again, the negative sign is because we want positive rates of reaction by convention. So if it's a reactant, that's going to decrease. The rate will always be the negative of whatever the delta concentration. What if we want, so here's the balanced chemical equation. 2N2O5 gives us 4NO2 plus O2. So if we're just worried about the decomposition of N2O5, what we saw on the last slide is perfectly fine. But how do we relate that to, say, the formation of O2? Well, notice that 2 N2O5 disappear for every 1 O2 that is being appearing. So if you want to relate the rates of these two things, you have to be really careful. So the rate of O2 increasing, so delta O2, delta T, actually is half as much as the decomposition of N2O5 because the N2O5 is decreasing, well, it's decreasing twice as fast, so the rate is equal to, the half of that is equal to delta O2. So notice the two things. Because the N2O5 is decreasing, we put the negative in front of it. And then to compare it to anything else in the balanced chemical equation, we have to divide by the coefficient. So because the O2 has a 1 in front of it, we just leave it as it is, delta O2, delta T. But because it's N2O5, there's two of them, we have to divide by 2 to make the rates equivalent to each other anyway. And then because N2O5 is disappearing, we put the negative there to make it a positive number. So these two are equivalent in this balanced chemical equation. So there, since 2 moles of N2O5 decompose for each mole of O2 formed, the rate of decomposition of N2O5 is twice the rate of the formation of O2. So you could multiply by 2 and change this around, but the easiest way to make them equal to each other is then just to divide by the coefficient. So if we wanted to say how is this related to the increase in NO2, we would have to say delta O2 over delta T equals 1/2 negative delta N2O5 over delta T equals 1/4 delta NO2 delta T. So if you want to again, so delta O2 over delta T is equal to 1/4 delta NO2 delta T, because the NO2 is being formed 4 times as fast, and so you have to divide it by 4 to make it back equivalent to O2. So here's the generalization, what I was sort of talking about. So if you have any balanced equation, if it's a reactant, put the negative sign in front of it, and then no matter what, if you're comparing it to any other reactant or product in an equation, you have to divide by the coefficient to make them equal to each other. And like I said, you don't have to do this if you're just focusing on one, but if you're trying to relate them to others within the same equation, you need to do this. So notice that I've got negative 1 over A over delta T equals negative 1 over B over delta T equals the positive of 1 over C over delta T equals the positive of 1 over D over delta T. To make another example here on the bottom, if you want to relate the rate of the I3 negative, which is a product, to the rate of the I negative, which is a reactant, you can say, okay, so the delta I3 negative over delta T, because that's a product and the coefficient's 1, will equal negative 1 over 3 delta I negative over delta T, because that is a reactant and there's a 3 in front of them. So what else would this equal to? It would equal to negative delta S2O8 over delta T. It would also equal positive 1/2 delta SO4 negative 2 over delta T. So you always, to combine them, or to compare them, you always use the coefficient, divide by the coefficient. All right, so in order to find the rate of a reaction, you have to measure it. You can't just look at a reaction. This is a really important thing to remember. You can't just look at a reaction and be able to predict what the rate's going to be. You have to do experimental data. And so obviously, well, we may do it in lab, but for some of these problems here, we're going to be given data. All right, so anyway, how can this right now we're just going to talk about what are some ways that you can determine the rate of the reaction if you're doing a reaction. One method is to have the reaction going on, and then withdraw samples from the reaction at various times to measure what the concentration is. So that's sort of what they're showing you here. So you can have the reaction taking place, and you can take samples to measure the concentration at various times. A convenient technique, in which we may be able to do in lab, is to look at color changes. So if a reaction actually has a physical property like a color change or like a pH or something like that, you can actually measure how long it takes for that color to appear or disappear or change or whatever. And that's usually a nice way to measure the rate of a reaction. So just some more examples. Gas phase partial pressure. If you're able to measure the pressure of one of the gases, you can do pressure readings and find out what the different partial pressures are. So that tells you what the concentrations are. And so you can measure over time how the concentrations change. And similar to what was on the last screen, colorimetry is a way of looking at colored compounds that change over time. And so you could do it visually, like that last slide sort of implied, that the color is kind of decreasing over time or increasing over time. Sometimes you can't necessarily see it, but you can use instrumentation to measure color changes by using some instrument called ultraviolet, if it absorbs in a certain range, ultraviolet or infrared or something like that. Or even the visible spectrum, you can measure things, and we may be able to do a lab like that at some point. So anyway, here, this colorimetry, the HO negative ion absorbs light near 400, so it may not be a visual, like I said, you can't see it visually, but you can put it inside an instrument that will measure at that wavelength. And so the more that's there, the larger the absorption, and so you can measure the concentration that way.